Well, hello, thank you for watching this video. I am Ana, and I'm from Universidade Federal de Ceará, and this is a joint work with Andrea Marino from Universidade de Studi di Firenze, and I'm going to talk about Eulerian walks and temporal graphs. Well, to begin with, we need to know what a temporal graph is. Well, you can think of it just simply as a graph that changes over time, but more formally, you have a pair, G lambda, where lambda is a function that tells you when each edge is going to be active during the lifetime of the graph. And also you can see it as a sequence of subgraphs of a graph, right? So here is an example. You have the basic graph is this one, G, and you have the first one, the second one, so just a sequence of subgraphs of G. And each graph in this sequence will be called a snapshot. And finally, we are working in finite things, so there will be a maximum over all the values in which an edge is active is going to be called the lifetime, the maximum value in this function. Okay, so these graphs have been studied under other names like dynamic networks, time-varying graphs, evolving networks, link streams, etc. And well, there might be some small variations. Actually, they're not exactly the same definition as the one I gave to you, but they change very little, and usually you can transform one into the other. Well, the natural questions here, of course, are what natural adaptations of graph theory concepts can be made, right? So you take a classical definition in graph theory, and you try to define what this would be in temporal graphs. And of course, again, you want to know which polynomial results carry over. And I must tell you already that they almost never do. And indeed, the adaptations of Eulerian trio that we did, none of them is polynomial time solvable, in contrast with the classical graph theory concept, right, which is easily testable. Okay, so let's move on. Before I show you my results, I would like to take a look at temporal paths, because then we can even see how these structures are different from the classical graph theory. So a path here, of course, you want that it respects the flow of time, right? Because so suppose that this edge here was active in time 3, you wouldn't want to accept this as a path, since it would mean that you left in time 3 and then you went back in time to use this edge. So this is not allowed. So a path must respect the flow of time. And when you define a path like this, then you can have many different notions of minimality. You can talk about the shortest path, which would be indeed the one that uses the least number of edges. You can also talk about the earliest arrival time path. So this one would be better, right? Because it arrives there in time 2. Instead, the previous one arrived in time 3. You can also talk about the latest departure time. Maybe for some reason you want to delay your departure as much as you want, as much as you can. And also you can talk about fastest paths. Okay, so all of these concepts are polynomial time solvable, and these 3 were first proved to be polynomial in this paper in 2003. And the fourth one was introduced in this other paper, more recent paper, where they also investigate the other 3 variations, giving better algorithms. Okay, but as I told you, many easy problems become hard. So for instance, connected components, finding 2 vertices joint paths, finding a minimum vertex cut, and this already gives you a hint that Menger's theorem will not work. And more recently, myself, Victor Campos, Raul Lopes, and also Andrea Marino, we proved that Edmond's theorem also does not work. Well, and after working on this for a while, right, I was really curious. Okay, Edmond's theorem does not work. It's interesting, but it's already a little bit more complicated concept in graph theory, right? So I was thinking, let's just go back and to more basic, more trivial definitions and see if they continue to be easy, right? And a better place to start than the Königsberg Bridge problem, which is maybe considered the oldest result in graph theory. And well, the problem was like this. So in this city, back in the 18th century, it had this river, right, which was connected in these small islands, which were connected through bridges like this, right? And the question was, can we go around, do a walk in the city in a way to visit each bridge just once? So this was answered negatively by Euler. And to answer this, of course, the first thing that he did was to ignore the geographical disposition of the bridges, and he looked just to the graph. And let's take a look. Right? So this graph here represents the disposition. Indeed, here, A and C are connected by these two bridges here, and we just add two edges between these regions. And now let's see why we cannot do that, right? It happens because the intermediate vertices in a trail. So you have to start the trail in some vertex and finish in some other vertex V, right? So all the intermediate guys must have even degree, right? Because if you pass by A, for instance, once, you pass through an edge and left through another edge. So each time you pass by edge, you will use two different edges incident to it. So in total, if A is not U nor B nor V, then it must have even degree. And here this graph has 4 odd degree vertices. So this means that nobody can be an intermediate vertex, and therefore you don't have the desired path, right? The desired walk. And well, Euler, what he did, prove that this is also a sufficient condition, and it's really not hard to prove this. It's one of the most basic results in graph theory. You can see this in any graph theory course, and it's very nice result, very easy to understand, and really considered to be the earliest graph theory result. Okay, so that's what we wanted. We were interested in it, and of course the first step was to check whether this was already solved. And indeed we found a paper by Eulerian from back in 84, where he gave also very easy and nice, easily checkable characterization of Eulerian graphs, but in this model here, what he called dynamic graph. But this was very different from temporal graph. In any way, Mikhail said this in this nice survey. He said that the results proved for it, the dynamic graph model, are resounding and possibly give some first indications of what to expect when adding to combinatorial optimization problems at time dimension. So I think that what he meant by this is that the result by Eulerian suggested that the problem would be easy as well on temporal graphs. But as we'll see, this was not the case. And also that you have at least a clue why they differ so much is because this dynamic graph model, it is actually just a model to talk about an infinite graph, and it allowed for edges to go back in time. Okay, so we started to investigate, right, what happens in our model. And our first interpretation was the direct one. Let's just call an Eulerian temporal trail a trail, so no edge repetitions. I cannot go back in time, of course, and I visit all the edges. So for instance, in this graph there, this could be an Eulerian temporal trail, right? We start here, visit all these red edges, finish in this guy, and then we start in this guy and finish here. Okay, so an observation is that having at most 2 odd degree vertices is necessary, of course, because again, you cannot repeat edges in the intermediate vertices. So the intermediate vertices must have even degree. But it's not sufficient. Indeed, we can see here an example. Here, these 3 edges appear only in G1, so you must do this in the first snapshot. But now in the second snapshot, it doesn't matter where you started or finished. The point is that you must also visit this edge and this edge which means that you will have to use this edge a second time, which is not possible. Okay, and as I told you before, indeed, deciding whether a temporal graph has such a trail is an incomplete problem, even if the lifetime is true. But I'll not show you the reduction. I'll show you the reduction for our next interpretation, which can be modified in order to prove this result. Okay, so let's take a look at our second interpretation. Here, we decided to lose a little bit the constraints, right? So we don't want that the entire thing is a trail, but only locally it's a trail. So we'll call an Eulerian temporal local trail a walk that cannot go back in time again, but that when you look at it in a given snapshot, it must be a trail. So you can repeat edges as long as you don't repeat the same snapshot. And again, of course, that visits all the edges of G. So this graph here, which was a negative instance for the previous interpretation, now you can do it, right? With the second one, because you can do like this, and then just visit the remaining edges in the second snapshot, like this. Okay, and okay, so let's take a look at the reduction for this problem. Before I start, let's just make some observations. The first one is that now having at most 2 odd degree verses is not necessary anymore, so the positive instances here will be a bigger class of temporal graphs. And this is why the intermediate vertices, because you can repeat the edges, you don't have that property, right? That all the edges that you use on them are distinct, so they might have odd degree as well. You can also take a look at it as just a collection of trails that together cover the edges of a graph, but with additional constraints, right? Because you need to glue them together. So in the first snapshot, you have something like this, right? You start in a vertex U, finish the vertex V, and then in the next one, you have to start here in V. So it's just not a collection of trails, but they must kind of sew well together, right? And another more important observation is this one, that if you consider a graph with lifetime 2, and you consider that you have a circuit means that you start and finish in the same vertex, okay? So it means that you started here on vertex U, finished in a vertex V, and then you started in V and go back to U, so it's closed. You start and finish in U. So if this happens, then each local trail must contain all odd degree vertices indeed, because if you have an odd degree vertex, suppose W, that is not in this trail, so none of the edges is visited in the first trail, then it means that only an even number of edges incident to it can be visited in the next trail. So of course there will be some edge that will not be visited, which is a contradiction, and this cannot be an Eulerian trail. Okay, so this observation gives us a strong hint that the problem is NP-complete, because now if you have that G1 is just G1 and G2 is the same graph repeated twice, and G is a cubic graph, then this observation means that I have to have 2 Hamiltonian paths, right? That together cover all the edges of G. This sounds very hard. Already finding one Hamiltonian path in a cubic graph is hard. Well, but this is not a reduction, right? This is just a hint that it's hard. But we made a reduction, an explicit reduction, that indeed tells us that the problem is hard even if your graph is just the same graph repeated twice. Okay, so meaning that the labeling function is 1 and 2 for every edge. Okay, so let's take a look how it works. So we are making a reduction from not all equals 3 sat, and we'll have this is the gadget related to a variable xi. And the idea about this gadget is that you will come inside of this gadget through an edge here, and you have to choose in each trail if you go through the upper path or through the lower path. So the upper path will be related to the positive occurrences, and the lower path to the negative occurrences. So these, of course, will be the gadgets of the clauses containing xi positively and these ones containing xi negatively. And if you have the property that when you go inside the clause gadget through this edge, you must go outside through this other edge, then you have the property that I told you, that you can only use either the upper or the lower path, meaning that that will give you the value of the variable xi. Okay, and the way you glue together is like this. You will just link all the gadgets related to the variables in a sequence like this, and you link the first one to the last one, and you add three pending vertices like this, and this is just so you can control where you start and when you finish, because if you have this, then you must start, because remember that all the odd degree vertices must contain in both trails, right? So one of the trails must be like this. Sorry. Yeah, like this, finish here. And the second one will have to start there, go around again, visit the other side of each variable gadget, right? And then come back and finish in the third guy, okay? So both trails must look like this. And what is left to see is how you ensure that indeed when you go inside, right, a clause gadget through this edge, you must go outside through the other edge. So let's take a look at this. To do that, we'll use this small gadget, which we call first edge gadget, and this is because the only possibilities of visiting these three odd degree vertices are like this. You must, in one of the trails, you must choose this path, and in the second trail, you must use this one. So these two edges here, this one and this one, always occur. So you can look at them as, look at this gadget as an edge between U and V that always occur in both trails. And that's what we do like here. So the red edges is just this small gadget. And now what we want to prove is that, so these edges here are the edges related to one of the literals in this clause. And what we want to prove is that this edge will be in the trail if and only if this other one also is in the trail. So suppose it's not, suppose I use this one and not this other one, because this guy must have even degree, right? Because you saw that I go around everything, so everybody here, so these are the endpoints. So every other vertex must have even degree. Okay, so continuing, this guy must have even degree, so I must use either this edge or this edge. Suppose that I use this one. Then it means that this one cannot be used since this edge is forced. But now this guy must also have even degree, so this means that this edge is used, but now this guy has odd degree. This cannot occur. And if instead I use this, again, cannot use this, must use this, and this guy again will have odd degree. So this is it, and the way I adapt this for our first problem is just that we know exactly which edges are being used in both trails, so replace those edges by two paths like this. So the edges that are being used twice, I just replace by this, so it means that in one of the trails you use the upper path, and then the other one you will use the lower path. Okay, and I do that also for the first edges. Okay, but what if we don't put any constraints at all, right? So now our third and last interpretation is, let's just be happy with a nice walk, right? Let's just do a walk that visits, temporal walk, right? We can go back in time, but that visits all the edges. And indeed, it might not be possible. So this is an example, right? So these three edges occur only here, and you must choose in which one you will start. So suppose I start in this one, then there is no way that we can go back in time to visit this one. So this already gives us a hint that the problem can be solved in this time here. So we can prove that it can be solved in time n to the power of t, where t is a lifetime. And this is just because the problem can be reduced to choosing for each snapshot, right? So suppose you have many snapshots. But it can be seen as choosing which of the components I'm going to visit all the edges, because if I decide to visit one edge in this component, then I can visit everything, right? But I have to decide which component I'm going to take. So if I just choose which component for each lifetime and see if together they can be arranged, right? Can be combined actually in order to form a temporal, Eulerian temporal walk, then the answer is positive. So if you do that for all the possible combinations, you can solve the problem. This is very easy. But unfortunately, in general, the problem is NP complete, and even if each snapshot is a forest of constant size. Unfortunately, I cannot show you this edition because of time constraints, but it's not very complicated. And I must say that it was surprising to me, because I thought that this one would be, at least this one would be easy, but indeed it isn't. Okay, so summing up, we have proved all of these results. Let me first bring attention to this line here. So we called a dynamic-based graph is just a graph that is repeated, the same graph repeated many times. So all the snapshots are the same graph, are equal to G. And in these graphs here, the walk problem and the trail problem become easy, because it's just a matter of either being connected here for the walk or being Eulerian for the trail. But the local trail isn't complete, as we saw previously. Looking at the general temporal graphs, we have proved that the Eulerian walk problem isn't complete, but can be solved next speed time parameterized by the lifetime. But however, local trail is NP complete already for lifetime 2, as well as Eulerian trail. And these two results here were obtained by Bumpus and Meeks, and actually this was the best award paper in IWOCA, so I recommend you to also take a look at their presentation. Of course, they proved other stuff, but here, in order to combine well with our results, right, to fit well in this table, I'm citing just these two results. They prove that this problem, the Eulerian trail problem, is NP complete even when the true rates is equal to 2, but it can be solved in FPT time parameterized by this new width parameter which they introduced, which is called the interval membership width. Okay, so to finish, I just want to cite some open questions. Well, there are the obvious gaps left by this table. So for instance, is Eulerian walk FPT when parameterized by any of those mentioned parameters? Is local trail possible to parameterize by true rates or interval membership rate? Of course, by tau we know that it's parameter complete. Also, there are many questions that we can still pose here. I'm just going to cite some of them that I thought about. So you could ask, are there other variations of the problem, or what other parameters could be of interest? What if the lifetime is large and edges appear often? So this gives you a hint that the problem becomes easier. Also, can you characterize them anyway, right? The Eulerian temporal graphs anyway, even if the characterization would not give you a polynomial time algorithm, but maybe there is a nice structural characterization here. I don't know. So I think there are still many other questions that you can pose here. But more generally, I really wanted to find a nice basic graph theory concept that would carry over nicely for temporal graphs that would become polynomial and very natural, let's say. I'm still in search of that. this is also very interesting. You can ask about general promising techniques to be used here, because in general, really things become very hard very fast. So the true rate, for instance, is very bad here. Most of the problems are already hard on trees, and could be promising the way it's introduced by bumpers in mix. So why not try that more? The interval membership weights could be a good candidate here. And actually, there are many open problems here, so I would say that you can just think about your favorite problem and go there and see if it's solved, and otherwise, what can you do, right? That's it. Thank you very much for your interest. I hope you enjoyed, and see you at the conference.